So floating point and shifting. Our first video is going to be on the general knowledge you need to have about floating point representation. And at the end of this video, we're also going to explain how you convert a decimal number to binary floating point number. And we're going to do that based on a couple of examples. So, floating point representation, what does it mean? The best way to understand it is by using again an example, which, as you can see here, again, we're using the speed of light. There are multiple ways that you can represent the speed of light with a floating point representation. You can either call it 3 times 10 to the power of 8, or 30 times 10 to the power of 7, or 0.3 times 10 to the power of 9. What we've managed to do by using a floating point number is that we have unlocked the decimal point position. And every time what we do is that we need to adjust the exponent of a base, which is always implied to be 10. A few more definitions here. In our example, this is the Mandisa, and this is the exponent. And the base is always implied to be 10. So let's see how things are now in the binary format. And more specifically, let's focus on an example using 5 bits. Both the Mandisa and the exponent will be bit strings, and the implied base is going to be 2. In this example, we're going to use 3 bits for the Mandisa and 2 bits for the exponent. The floating point representation is going to use the 2 least significant bits as the exponent, and the 3 most significant bits, the 3 more significant bits at the beginning of the bit string, as the Mandisa. So the range is changing a bit compared to what you know. If you assume a fixed point representation, like the one that you've seen so far before today's lecture, the range is between 0 and this number over here, which in decimal is 31. And overall, you got 32 numbers, from 0 all the way up to 31. If you count those numbers, they are 32, or otherwise 2 in the power of 5. Now, by unlocking the floating point, the representation spans from 0 to this number over here, which is 56. Now notice the difference. We had numbers that span between 0 and 31, and now numbers that span between 0 and 56. In the next slide, we're going to explain where this happens. So again, we see that with fixed point representation, this is the range, while with a floating point representation, this is the range. Now there's a question here. We're using, in the general case, n bits, which means that with those n bits, you can always have 2 in the power of n combinations. In our example with 5 bits, this means 2 in the power of 5, which is 32 different possible combinations. Why does the range change? Well, it's because the values are more scattered. Not every value is represented here between and including 0 all the way up to 56. Whereas here with the fixed point representation, all the integers between and including 0 up to 31, they're included, they're represented. So the values are more scattered, which means that there is a trade-off here. You increase the scale at the cost of less accuracy, because not every number between 0 and 56 can be represented. And even worse, you've got numbers like 16, which can be represented with 2 different ways. In this first way, we're using 4 as our Mandisa and 2 as our exponent, while in this case, we're using 2 as our Mandisa and 3 as the exponent, and they both represent exactly the same number. This is a redundancy which aggravates the problem of scarcity. So not only our numbers are scarce, but some of them are represented twice. This is wasteful. Ideally, what you would want is to have only one representation for each number in the decimal system. There is a solution to that. As we say, we normalize the floating point representation, and the way to do that is by fixing the first bit of the Mandisa being always equal to 1. The equivalent of this range, regarding the Mandisa this time, is going to be over here in the decimal system, anything between 1 all the way up to 2, or almost 2. Let's try to understand this better. So the Mandisa, which is the first 3 bits, spans between 1.00 and 1.11. The exponent, on the other, spans between 00 and 11. Now, this implies that the minimum value that you can have with this floating point representation is 1, and the maximum one is 1.11 times 2 in the power of 3, which in other words means 1.75 times 8, which is 14. So the minimum value is 1 and the maximum value is 14. And that comes as a direct consequence of fixing the Mandisa, the first bit of the Mandisa, the most significant bit, to 1. But notice that we have a small problem again. So we fixed the first bit to 1 to solve one issue, to avoid having numbers being represented more than once in the binary system. However, now that we got 4 available bits, instead of having 16 different binary words, we have a range from 1 all the way up to 14, and that also includes the fractions. So in order to fix this problem and get advantage of all the bits that we got available, what we do is that we use the hidden bit technique. So now we imply that the first bit is always 1, but we don't keep it anywhere. We do not store it anywhere. So this means that the numbers are now like this: 0.000 times 2 in the power of 00. And then you got 32 possibilities because you can take advantage of all those 5 bits. While previously, you only had 16 possible combinations. So overall, up to now, 2 things to bear in mind. The first one is that we fixed the first bit of the Mandisa so that we avoid representing a number from the decimal system more than once in the floating point, in the binary floating point representation. And then, since this is always implied, we do not store it anywhere. We do not store the most significant bit. We imply it, and then we use the rest of the bits in any way that we want to, so that we increase the number of possible combinations of these bits. Now let's switch to reality. The previous ones were examples for you to understand what the binary floating representation is, floating point representation is. Here, I'm going to give you the IEEE standard for CPUs that use 32-bit floating point numbers. According to that standard, the first bit is used for the sign. The next 8 bits are used for the exponent, and the remaining 23 are used for the Mandisa. So overall, we have 32 bits. Now at this point, I challenge you to pause the video and think what is the range of numbers according to the standard. So how do you convert a decimal number to a binary floating point number? Let's now see how you convert a decimal number to an 8-bit floating point format. We're going to go through all the steps of the algorithm using this particular example. We're going to convert number 2.625 in the decimal system to an 8-bit floating point format according to this format over here, where the most significant bit is used for the sign, the next 3 bits are used for the exponent, and the last 4 bits are used for the Mandisa. So always the first step is to convert the absolute value of the number to a binary. The particular number is easy. The integral part is straightforward, while for the fractional part you need to go through the process of continuous multiplications that we've shown to you during week 2. Now if you do that, the binary representation of 2.625 is 10.101. Now the next step is to append times 2 in the power of 0. You may wonder why we do that, because it's like multiplying with 1. 2 in the power of 0 equals 1. Well, this is an intermediary step for the next one, which is the normalization. Now pay attention to what has changed here. Hit the pause button and try to identify a pattern. What we did is that we moved the point 1 position to the left. Now, as we're going to explain next in this series of videos for week 4, by moving the point 1 point to the left, 1 position to the left, this is equivalent to dividing by 2. Therefore, what we do is that we increase the exponent by 1 in order to reverse this action. So if we divide by 2 and then at the same time we multiply by 2, the result remains the same. Now, in the more general case, what we do is that we move the point as many times as needed until it gets before the first digit. In this particular example, we only need to move it by 1 position, which means that we increase the exponent only by 1. The next step is to find the Mandisa. Well, we go back to the result of the third step, and things are very easy. We just omit the leading one. And that's your Mandisa. Now, if your Mandisa had less than 4 bits, you would have been filling up with zeros on the right as a suffix. In our example, we don't need to do that because the Mandisa is already 4 bits. Then we need to find the exponent. Now, in order to do that, we need to add something which we call bias. Take a moment to look at this. In the general case where you got k bits used for the exponent, the bias is equal to this number over here, 2 in the power of k minus 1 minus 1. In our particular example, we use 3 bits. Therefore, the bias is equal to 3. If you've done that, then computing the exponent is very easy. You just take the exponent from the previous step, which is 1, and you add 3. The result, you convert it to binary, and here you got your exponent. Now, for the IEEE 32-bit standard, we use 8 bits, therefore the bias in this case is 127. And the final step is very easy. We use 0 because the sign is a plus. This is a positive number. So with this example, we went through all the steps, the algorithmic steps, for converting a decimal number to an 8-bit floating point format according to the format that we use here. Now let's see again the same example, only this time let's look into a negative number. We're not going to go through all the steps one by one over here. We're going to do things faster this time because you've already seen the process. We're going to find the integral part, which is 4, and this is pretty straightforward. Now, regarding the fractional part, we need to do these multiplications over here. If you would like, pause the video at this point in time and just remind yourselves how we do this. Therefore, the result in binary format is 100.11. Now, the next step is to multiply by 2 in the power of 0 and then do the normalization. If you remember what we said from the previous slide, and if you read again here what we do for the normalization, we need to move the point as many times as needed before the first digit. So in this particular example, we're going to move it 2 places on the left. This means that in order to balance the change that we did, in order to revert the change, we need to increase the exponent by 2. Also, now we got available the Mandisa. The Mandisa over here is nothing more than just getting rid of the leading one and keeping the rest. As for the exponent, we take the 2 that we previously found, that was the exponent from the previous step. We add the bias, which as we know from the previous example is equal to 3. In the more general case, it's equal to 2 in the power of k minus 1 minus 1. And that gives you an exponent equal to 5. As for the sign, since this is a negative number, the first and most significant bit should be 1. Now, with those 2 examples that we just shown to you, we've covered both the case of a positive and of a negative decimal number being converted to our 8-bit floating point format.